Morning, everyone. Gyanin. I'm part of the engineering team here. So, it's so encouraging to see so many of you on a Saturday morning, right? It's not very easy. Usually, people partying on Friday night. This shows that all of us have a learning mindset. That is something on which we thrive in Zomato. We want to share as much as possible. We would want to hear from all of you so that all of us grow and the engineering talent, the data platform knowledge grows in our country. Right.
Yeah, so hi everyone. My name is Kartik. I'm engineer at StarTree. With me is Jayesh. He's solutions architect at StarTree. And today we'll be talking about real-time analytics with Apache Pinot. So what is Apache Pinot basically? So Pinot is in simplest form is a OLAP database. So you have two major databases. One are OLTP, which are like MySQL you use for transactions. And then we have OLAP databases, which are used for analytics purposes. So a good example will be something like Hive, where you run complex queries on data stored in S3. And then you use that data to basically for the product analytics. So Apache Pinot is designed to consume data from real-time sources. So what do I mean by real-time sources? It's the data streams, for example, such as Apache Kafka, Apache Kinesis, Alzar, Google PubSub, or anything else. So you can simply consume that click stream. You don't need to go through whole storing it into S3 and then like basically running a whole heavy query engine on top of it. You can directly query that data as soon as it is available. We have also designed Pinot to be used in user-facing applications. So what that means is that your query latency should be in single-digit or double-digit milliseconds. You should not have to wait like a couple of seconds for the results to arrive, which is the general expectations with the analytics databases. So again, Pinot has like normal SQL interface. You don't need to like use any complex JSON or anything to query. You can just use normal PostgreSQL, Hive SQL, and stuff like that to query the data. So one of the major things Pinot is designed to use for is like link. For example, in LinkedIn, you see who's viewed my profile, you see your whole feed, and basically the talent insight dashboard as well. So all that is powered by Pinot itself. So in fact, Pinot was designed first as LinkedIn only, and later on, like once it was better tested inside LinkedIn, it was open source for the general user base. So currently, like these are like the major customers that use Pinot. You can see Stripe, Uber, Walmart, Target, Razorpay, LinkedIn. And in fact, like Stripe is, I think, has the largest cluster running currently. They have around 1 trillion rows in a table or something with a couple of petabytes of data. And like they have been contributing a lot to the open source distribution as well. Yeah, so let's go over the architecture of Pinot. So Pinot basically consists of 5 major components. First is the servers, the controller, the broker, the minions, and the zookeeper. So the servers are basically the ones that do all of the heavy lifting inside Pinot. What basically, whenever you consume any data, that data consumption runs through servers. The data is stored inside the server. Whatever query you are firing will be run by the servers itself, because since they have the data, they can only answer your queries. So these are the components which you generally need to horizontally or vertically scale inside the cluster. The data, whatever is stored inside Pinot, is in the form of segments. So segments are nothing but basically small tar files, and we just chunk the data into a couple of rows, make a tar file. In that tar file, there is generally metadata as well. That metadata can contain, okay, this particular chunk has the following columns. The columns have these min-max values. These are the indexes created on top of the columns. And that tar file is then stored inside each of the servers. Apart from storing it inside the servers, we also store it in a deep store. That deep store, you can configure it to be S3, Azure, or Google Cloud Storage or anything else you like. The second major component is the controller. Controller is basically the coordinator of whole cluster. Whatever queries, whatever API operations you will run, like creating a table or deleting sub data or assigning role-based access policies, that will go by a controller only. And controller is responsible for basically monitoring the whole state of the cluster. It will see, okay, these are the servers that are live. They can serve the queries. These are the servers that I need to launch. These user has created a particular table. So where does this table need to reside on this server? So all that is taken care of by the controller. The controller uses Apache Helix inside it. Helix is just used as a message queue sort of, powered by the Zookeeper behind it. So for example, if controller needs to communicate something to the server, what it does is that it simply publishes the message inside a Zookeeper. Okay, do this particular operation. For example, elevate the status of segment underscore one from offline to online, which basically means this segment is now queryable. So that message will be published inside the Zookeeper. Zookeeper will, the servers keep on listening to the Zookeeper as well. And then like they'll detect, okay, this is the message for server one. Server one will take care, will basically try to execute the operation, whatever is defined in the message queue. If it's able to successfully execute, it will delete that message from the Zookeeper. Okay, I am done. I have completed this operation. If not, it will simply update an error message. Okay, and then controller needs to take care of what to do with that error message. Should it pass it on to the user? Should it take another action on after this error message or anything else? The third component is the broker. Broker is where like the high level queries, whatever user, basically if user needs to run any query, they will go to the broker. What broker do is that they have a very simple operation. You provide a standard SQL. They will compile it to something like which is understandable by Pinot. They will compile it into an execution plan. And then like based on that execution plan, they will forward that query to the servers which are eligible. To decide which servers are eligible, like they communicate with the Zookeeper, they fetch all the metadata, okay, for this particular query. The segments are located only on server 1 and server 2. So I don't need to send any query to server 0. Just I'll forward this query to rest of the servers. The rest of the servers will run that query. Whatever reason, they don't communicate with each other. They just run their own queries and return the results back to the broker. Now, broker will take care of compiling all of the results, reducing them, basically any summation aggregation that needs to happen. And then like they will return it back to the user. The fifth major component is minion. So what minions are designed to do is start like basically all of the ad hoc scheduling operations. So for example, you can say to Pinot, okay, run a particular ingestion task whenever this particular file arrives in S3, or run something once a day. For example, clearing the data of this table, which is more than 100 days old. So all of that tasks are scheduled inside the minion. Minion is purely an optional component. If somebody doesn't need to deploy, they don't need to. And in fact, before minions were there, all of these operations were done by the servers only. But what it led to was like people had to scale up servers a lot, and like there was no way for them to downscale. So with Minion, that it's possible that they can even enable auto scaling on top of it based on the task. So for example, you have like a data dump in S3 which arrives once a week, but it is like hundreds of GB, or so you can simply run auto scale on the Minion to scale it up before that ingestion task is fired. And then like once the ingestion is done, you can downscale it. And that is in fact even manageable through Pinot deployment itself. So yeah, so let's go over the basics of real-time ingestion, like how it works in Pinot. So first of all, like user will, for example, say, okay, I want to create this table. That table will generally contain the schema. What is the format that data is coming in? Is it coming in JSON? Is it coming in protobuf? what are the columns that are present in that data. It will also contain the configuration to connect to the data sources. For example, if you're Kafka, it will contain the brokers which you need to query, the topic name, the offset, reset, and stuff like that. And then it will contain anything else like the indexes you want to create on top of that table. So once that request arrives to the controller will check, basically query the Kafka. In the Kafka, it will determine, okay, this topic has 3 partitions, for example. So now in Pinot, the real-time ingestion works on the partition level. It doesn't work on the high level. So you have, if by that, what I mean is that each server is responsible for consuming from a particular partition. It's not like all servers are consuming just from the Kafka, and Kafka is responsible for maintaining the offsets. It's Pinot's responsibility to maintain those offsets and to basically know, okay, I've consumed till offset number 50 from partition number 0. So next time when the partition resumes, I have to start consuming from this particular offset. So controller will determine, okay, as in the request, we had 2 replicas and the Kafka topic return 3 partitions. So what controller will do is that it will create a sort of a state. This state resides in the zookeeper. So in that state, what it will do is that it will basically assign each partition. And since we have replica 2, so 2 servers need to be consuming from the same partition. So what it will do is that it says, okay, partition 0, server 1 and server 2 should be consuming. Partition 1, server 2 and server 3 should be consuming. And for partition 2, server 3 and server 1 should be consuming. Once it has created this state, it simply updates in the zookeeper by helix again. Now servers will keep on listening to this state, and it will also pass the, like in the message key, okay, you should start consuming now. The servers will keep on listening to this state. They think, okay, they are now they have got an instruction from the controller that we need to start consuming. So they will create the consuming segments in each one of them. Like, so server 1 was assigned partition number 0 and partition number 2. So server 0 will start consuming from both of those partitions. Similarly, server 2 will start consuming from partition 0 and partition 1, and server 3 will start consuming from partition 1 and partition 2. So now what happens is that once you can define in the table, like when should like a segment needs to be created. So you can define it like, okay, when server is done consuming, for example, X number of rows, or the total data size is like a couple of gigabytes, or you can define based on time, okay, 1 hour has passed or something like that. Once that time duration has passed, what each of these servers will do is that like they will simply take the offset till which they have consumed the data, and they will report it back to the controller. Okay, I have created this segment, and this particular segment contains the data till, for example, here server 1 says I have the data till offset 100, and server 2 says for the same partition I have the data only till offset 80. So now what controller will do is that it will run the logic and it will determine, okay, which one has the correct state. So for determining the correct state is it's a complex logic. We call it the commit protocol, but for the simple term, we can assume like the largest offset wins. So here we can say, okay, since server 1 has consumed till offset 100, so controller will say, okay, server 1 has the true state and server 2 doesn't have the true state. So it will simply send the commit signal to server 1. Server 1 will then commit that segment. It will upload it to deep store, which is S3 or something like that. And then like once that is done, the segment is marked as online. That means that segment is now present as a proper tar file with all the indexes and stuff. And then it can be used in the queries as well. So once that is done, like the server 2 will, controller will say server 2, you don't have the true state of the segment. So you need to download it from the deep store because server 1 has already committed that. So server 2 will simply go to the deep store, it will download the segment and replace whatever data it has inside. And similarly, since partition 0, we have already consumed till offset 100. We will controller will again create a new key value in the state, and it will say, okay, now server 1 and server 2, please start consuming from set offset 100.
I have a question.
Yeah.
What is the rationale behind multiple server consuming from the same partition? Is it like when anyone gets success, it will dump into the deep store and another will sync, or it might be?
No, it is to maintain, like, we want to be able to query data as soon as possible, and you have the expectation that the replication should be whatever you have defined. So for example, if the consumption fails in one of the servers, so then like you will not be able to consume that data.
Reliability, the first.
Yeah, exactly. So you should be able to, like, there should be multiple data sources even for the whatever is being consumed currently, not just whatever has been stored. So that is the rationale.
What about the consistency of the data that is getting?
Yeah, so the consistency is like maintained through the commit protocol on this.
So when multiple servers are writing into the same deep store.
No, they don't write to the deep store directly. They first write to their local disk, and then like once controller decides which server is the winner, only that server will write to the deep store. It won't be like multiple servers writing it. Yes.
Is the consumption to 1 million, one task on whatever the unit is can ingest only from one person.
Yeah.
So do you ever feel there's a bottleneck on the ingestion because it's like there's only one task?
That basically task is pretty lightweight. What it does is that like it's simply just parsing the data from the whatever partition you have assigned, and then like it will just create the index and everything is handled later on. So that it doesn't have a lot of load. You can run like thousands of consumers in parallel inside a single machine.
Is there any so for example you transfer data from local disk to the deep store?
Yeah.
And the eventual point of data being on the disk is anything?
Yes.
If you pass it on to the deep store, then it has to be brought into the computer system from the deep store.
Yeah.
So the unit of data matters here because you don't want to bring a lot of data from the deep store. So how do you manage?
So we have two deployment options for that. One is where we always keep the data in the local. Even if we commit to the deep store, we don't remove it from the local, and local one will always be queried. And the data transfer happens in the form of segment only. You can't go much more granular than the segments. And another option is the tiered storage, where you can say is that, okay, keep all the older data in the S3 only. And for last 1 month or something, keep it in the local. And even for the older data, you can keep some of the metadata in the local. So that for example, you can keep some of the indexes in the local so that your queries are faster and you can do all the querying.
How large is one segment?
That is purely configurable by you. You can mention in the table. Generally, people create around 100 MB size, and not more than, generally no one creates more than 1 gigabyte.
Have you seen so the segment can be 100 MB, it can also be 5 MB. A 5 MB segment will have less data, but it will be faster to get in. So have you seen trade-offs?
Yeah, so after that trade-off only we have reached that 100 MB figure. But again, we have left it up to the users only. So basically we provide good defaults. But if you want to change, you can just change it by a table level. And that is configurable on the table level only because each table is associated with one particular data source.
Okay. So
Sorry, just to add, deep store is primarily for backup and recovery.
Yeah.
The queries are being served via the server nodes.
but that also means that those servers are always live because active data is kept there.
Correct. And correct. That is why we can guarantee the millisecond latency, right? As you rightly pointed out, if you always go to deep store to fetch the data back, load it into, let's say, the server and then push it up, you won't be able to guarantee millisecond latencies. If that is the trade-off you are okay with, as Kartik mentioned, there is another option of deployment where you can deploy the data or keep the data in deep store, which is S3, etc. But then you trade off on the latency aspect. And instead of milliseconds, it will be seconds or slightly more than that.
No, the idea is that there is like a room for optimization, where you can reduce costs on like the service that you maintain by
Correct.
optimizing the data push and fetch from the deep store. So that is the idea. Can you suggest the 100 MB segment size? 100 MB depends on like if the file is like a lot of columns, then and so I don't know, but
So see, first of all, the data is stored at the columnar level. So because it's a OLAP database, right? So if you query something, we already know, okay, these segments need not to be downloaded because they don't. Yeah, exactly. I think we can discuss this later on. Like I will explain. So there's one question on the chat as well. So the number of servers should always be multiple of number of partitions. What happens when Kafka repartition happens? So that needs not to be the case. You can keep like run all the partition consumer in the one single server as well. That is the responsibility of the controller to assign, okay, this partition needs to go on what server. If you have like, they need not to be the multiple. In case a repartition happens, the controller will detect that, okay, the number of partitions have increased. And like it will simply start the consumption for new partitions in new servers. Like that is purely like handled by the controller.
What is the role of replica here? Because generally
Replica is for reliability because you want to ensure that like in case one of the server goes down, then your data, like not even data. Yeah.
the question is like replica has been maintained by the Kafka end.
Yeah. So, but you are not
also reading the replica.
Yes, so but here you don't want to rely on the Kafka replication because you have already pre-processed, created some segment. If you rely on Kafka replica, then what that means is that in case the data gets lost here, you will have to reconsume all the data from the Kafka.
So replication happening on our servers also.
Yes.
What is the retention policy for the deep?
Retention you can define like it's in the table level only. You can define like generally people keep it to 7 days. Generally, people don't even keep any retention policies they want to.
Same for the deep state also.
Keep store, yes, exactly. Yeah.
Replica is also used for querying or is it just for?
No, for it is like there is no differentiation as such. Like it is in fact exactly same copy of the server. Like the controller would differentiate. Okay, this is a replica or this is a master or something like that. For it, everything is same.
But like while querying, you would essentially be only giving this segment addresses for the master node, not the replica.
No. All segments are equal. Like as is mentioned, the server does not know if it is a replica segment or a master segment. There is no master slave concept, if I may. All segment chunks are equal.
Because in few architecture, like they do the replica based on the time zone. So they put to reduce
That actually reduces the latency, right? Because you're waiting for the master or the slave to commit that I have the latest copy, etc. And that is the reason this is not done in that way. It will add a latency, basically additional complexity in the commit protocol saying that, okay, this is the latest segment versus master saying, okay, no, etc., etc. And that is why all chunks are equal.
Replicas on land. So if I'm filing the same query, then I can get different results depending upon which server is going on.
No, that is again handled by the controller as well. Like it would give you even for the live data, right? Where, as I mentioned, like one is consuming till 100, another is consuming till 80. And controller knows that, and they will never be the case where you get inconsistent results even during.
So, like this commit protocol that you mentioned, so once let's say S1 has been like known that it has the latest of
Yeah.
So what happens after that? The other like they replicate only from the deep storage, they don't consume from the topic, or like they keep doing it and this commit thing happens periodically. Like
So that you can define. By default, it's like they will discard everything and download the whatever the committed segment is from deep storage. But you can define, okay, if you have the latest data, why do you need to re-download it? Like that is configured.
Probably the question is the next time who will be eligible for committing to deep storage? Is it like keep on switching or this will work?
No, it will keep on switching. Every time the commit happens, the controller's responsibility is to
Yeah.
decide the winner. It's not like server 1 has been decided, server 1 will keep on committing.
How does the controller know the vintage of each topic?
It queries, first of all, like, for example, it will know from the Kafka itself. And then, like, what do you mean by like weightage?
By vintage means, let's say, one Kafka topic, preparing a segment is much costlier than another topic because of number of fields.
Yeah.
How does it know the weightage so that it can distribute the load equally among all subs?
It's the controller's responsibility, like, basically based on the number of partitions and the segment, like the size you have defined. It won't know like, okay, this segment, this particular topic now is receiving 1 Gbps of data, while the other one is receiving just 10 megabytes per second of data. That is not the controller's responsibility. That is the responsibility of the segment configuration you have defined. Like after, like, for example, 100 MB, you should like basically rebalance it or stuff like that.
In that case, like for example, let's say the orange color one is the high load. Like these two servers would be under very high load.
Yeah, so for that, what you can do is that you can go into the, like, if you feel like some server is like under very high load and controller is not managing it properly, you can simply go to the UI, click on rebalance table, and it will rebalance it across the servers. Because the data is already in the S3. So those, the new state will be created and the data will be equally partitioned again across all the servers. So for the query side, I have already explained, like the broker, if any query you fire will first go to the broker. The broker will simply go to the zookeeper to fetch all the metadata for the segments. So for example, it will fetch what is the earliest timestamp in the segment, what is the latest timestamp, what are the columns present, stuff like that. Then it will do the pruning. By pruning, I mean like which servers need not to be queried. And then it will forward the request to the servers. So that is what we call the scatter and gather. Yeah.
I think there are some people asking questions.
Yeah,
I'll answer them at the end. I think we are other people.
I'll reply to them in the meeting.
Yeah. So for the query part, like we simply perform like the queries are forwarded to the servers. The servers basically do all the processing, read the data, compile the results, and then send them to the broker. And then broker will simply like return whatever the response to the users. So
Is there a provision to do read-write separation? Like, I would want to have specific servers for read and specific for write. So, is that something?
I don't think so currently. It's basically equally distributed across all the servers. So for the query side optimizations, we support a lot of indexes. So the popular one are the inverted index, which are used for like where clause. So where column is equal to A if you want to get the results quickly for that. So we store the mapping of the in which rows actually the column A value is located. Then we have the sorted index, which is just the optimization on top of inverted index. Then we have range index for the queries, which are like where timestamp is greater than equal to T1, less than equal to T2. JSON index is something like, for example, you have some unstructured JSON coming in the Kafka topic. So you would need not define columns for it. What you can simply do is that just consume this JSON, and at the time of the query, I will define the column. Basically, I need to query particular, for example, value from this particular object in the JSON. So what it does internally is that it creates the indexes like on top of every field in the JSON by default. The text index is something like, in Elasticsearch or UC. So, and geo index is for the geolocation. For the aggregation optimization, like we have the normal hyperlog and theta sketches. And apart from that, we have like the StarTree index. So the StarTree index is simply like a compromise between the indexing and the like pre-aggregation. So for example, if you have a complex query, like some aggregation query. So generally OLAP databases will perform this aggregation whenever you fire that query. The another solution for it is that like you can simply pre-aggregate all the results. But what that leads to is a lot of basically space usage. So what we support is like the StarTree index. That's what StarTree index does is that like it pre-computes some of the data and creates a sort of the tree. And when a query is fired, what it will do is that it will simply combine whatever the pre-aggregated results it has, and whatever it doesn't have, it will compute in the real time. It will sum those up and return it back to the users. So this is the JSON index I was defining. So for the JSON index, as you can see, you can consume like a whole JSON. And like you can mention, okay, I need like in the where clause, I need the from the basically all the fields where the name is adding. But the name column as such is not defined. Is it present inside just a person object, and that is just a JSON string, nothing else inside the column. But you can clearly define it, and like the optimization is not on the query side. The query side is very simple. Like you can simply utilize any JSON library to extract out the fields. The optimization is on the indexing side, where it will already have the index where every field in the basically every person object has the name Adam. It will already have that data computed inside the segment. So next is the UPSERT ingestion. So that is generally one of the features that is not present in the OLAP databases. So for the UPSERT, like what you can do is that if you have define a primary key, you can choose to replace that basically whenever the new row arrives for that primary key, you can choose to replace that row. You can even choose to do partial UPSERT. So for example, only you can change one of the columns. You can sum of those values with the previous values, and all of that is supported. So for the UPSERT ingestion, like what we do is that, for example, we have rows with the primary key defined as A, B, B, C, C in one segment, and then like the another segment has this basically the primary key is E. So now what happens is that suppose in the Kafka topic we receive the primary key data again. So for example, for primary key BB, we receive the status has changed from assigned to pickup. So what Pinot will do inside is that it will simply update that data. The segments are immutable in Pinot, so it won't change anything inside the segments which have already committed. What it will do is that it maintains a valid doc ID index. So in the valid doc ID index, it defines, okay, what are the valid row numbers in this particular segment. So earlier it was saying that if you go on the previous slide, so this segment 1 had the valid doc IDs 0, 1, and 2, while the segment 2 had the valid doc ID 0. But after the UPSERT row, what we do is that we simply remove this old doc ID 1 from the valid doc ID index, because that state is not valid. And we simply assign that whatever the new doc ID is created to the segment 2's index. Again, like some new row comes which is inside the same segment. So for example, EE status is changed from pickup to delivered. We'll simply update the doc ID from 0 to 2 here in the valid doc ID index. But since the sealed segment is already that is present in the deep store, the mutable one is where the consumption is still happening. So here we can simply change the data in the segment because it hasn't been committed yet. So we simply change the data for E, like, okay, this particular row now has like, these are the values for this row. And then like, when the commit operation or seal operation is triggered, we'll be like creating the new segments, and those new segments will have the valid doc ID like attached to them. Like, for example, for the segment 2, the valid doc IDs are 1 and 2. And this metadata is currently like, you can choose, like currently it is only on if. And recently we have launched the off-leaf upsert as well. So there you can choose to put it in any backend you like. So for example, you can use any key values to do this.
So indexes are also updated by Upsert,
Yes.
but there are a lot of Upserts happening. Like if I want to do Upsert in batches, would that be edited in a?
Upsert in batches.
So my use case would be like I have TBs of data. I want to upsert some 100 GB of data within that TB data.
Yeah.
So how efficient is that?
So see, on the query side, like there are no changes. So in the query path, basically how it will work is that like for every row you want to upsert, it first has to check in the metadata. Okay, where is the old basically value located for that primary key? It won't change the old primary key, so that part is sorted. What it will do is that it will simply change the valid doc ID index that I mentioned. That index itself is maintained in the memory only, and like it's not part of the tar file that is generated. So there's no like as such heavy overhead for doing the.
So apart from memory, you would be maintaining it somewhere else at the backup, right? Like
Yeah. So whenever like there's this basically task runs. So what that task does is that like it will process whatever the valid doc IDs index it has into the disk in form of .snapshot files or something. So in case that data is lost, it can be and even if you don't have those .snapshot files, it can be recreated again, like by just reloading the table.
So that means like if I give a batch of upserts, it would be done on a row level only, or like a column level.
Yeah. The next thing is like the full SQL semantics. So earlier Pinot, like if you want to do joins in Pinot, you had to use the lookup tables. So lookup tables are like very simple, like you can define the dimension tables. For example, if for the order data, you simply have the user IDs. You can define another table which has the metadata for each user, like what is his name, address, and stuff like that. And like these are lookup tables, like the requirement was these lookup tables need to be located in the same server, like where is the whatever is the basically the main primary table is there. So that was not like very efficient. So what we are introducing, like we have started rolling out, is the So what we have started rolling out is the like a new query engine. In that query engine, what happens is that as I explained earlier, the broker simply forwards its query to the servers, and server returns its results to the brokers. But the servers don't communicate with each other. But in the new query engine, the servers also communicate with each other. The data shuffle happens, and so after that, like you should be able to do the full query, like any heavy joins you want to do on top of like this.
But isn't it going to add latency?
Yeah, so it is up to you. Like you can, at the time of query, you can enable or disable the query engine. You can select, okay, we call it the V2 query engine, use the V2 query engine for this query, and don't use V2 query engine for if you have some simple queries, because you don't want this latency as well.
But even in that case, also we still maintain the lookup tables in all the servers.
No, we don't. It's just normal tables, like the shuffle will happen. Yeah. So, any other questions? Yes.
So we were talking about like ingesting data from Kafka, but let's say the use case is 100 GB at once. Like I'm not doing I get 100 GB of data in one day. I need to ingest that. So how is that supposed? I think.
Yeah. So for that, like we have the file ingestion task that runs inside the minions, or you can simply run the Spark job. And like we have Spark connectors and stuff like that, where you can directly.
Since the server resources are limited, like they were scaled up to the read level, like are they scalable in runtime as well?
Yeah.
Sorry, the minion, if you specifically remember, there was a component which was minion mentioned, that there is an auto scaling enabled on that. So depending upon the task size, task queue, it can auto scale to basically handle that load. And from an offline perspective, it has native connectors to S3, GCS, delta leak, so on and so
The
forth.
data segment would be committed inside the servers, not the median, right?
Correct, correct. Yeah, yeah. The
So
minions is
servers
there
are-
for
or both horizontally and vertically scalable at runtime. Like you don't need to bother with that.
So let's say if I auto scale or descale the servers, how does the rebalancing?
Rebalance, like you, for example, you remove one of the servers, right? So the protocol for that is generally like we have tags associated with the server at the table level. So you first untag that server and then you click on the rebalance operation. So the once you click on the rebalance, Pinot will know, okay, server 2 is about to be deleted. And so it needs to move data. If some data is not available on server 2, it needs to move to the other servers. So it will do that rebalance operation. Once that rebalance operation is done, you can simply remove that server. Same for adding.
Spark. So any use case with Spark, because Spark is also a processing engine. So
This is not processing engine. This is a storage engine. Yeah. So you can do a whole lot of pre-processing in Spark or Flink, and then you can simply dump the data.
How scalable is the controller? Because I don't think it's a single point of failure.
Yeah. So for the controller, like you honestly need to vertically scale a lot. You can run the HA setup of the controller. So for that, but there will be only one primary controller, which is the leader at a point of time. That will handle all the things. But in case of that controller dies down, the secondary controller will like become the leader and it will take care of it. Generally, in the prod setup, we run around 2 to 3. The controller like doesn't deal with a lot of data. It's more on the like CPU side only. Like you don't. Yeah, so even in that case, like it doesn't need to like because it's only dealing with the metadata, and then metadata itself is like stored in the zookeeper. The operations are not a lot like so controllers we run are like not like really happy. Even in the deployments which are like above like 50 billion rows or 60 billion.
How is the fault coordination like on the broker level? Like
Brokers are simply like every broker is independent. You can simply horizontally scale it. It doesn't store anything. So it's like just your normal service, which you can scale it by Kubernetes, right? You can add pods or remote pods.
pre-compute, like the segments have the pre-computed data. Whatever based on the indexing, it is whatever the aggregation that we or roll up that we need to do.
Yeah.
It will have to store the data.
Yeah.
Then, if I say parent asks to get a certain result, now the broker will go and from all the segments it will take the data that is available. So what if their broker fails? How is the like massive, like which is say 1 year of a data that is looking into or something large? How the fault toleration happens?
Broker looks into the data in the whatever is stored in the zookeeper only. Like it doesn't look into anything else. Like it just needs to be concerned with the metadata. It queries that and it simply forwards that query to the servers. It doesn't do anything else. Like its only job is to whatever the SQL query you have given, just compile it into a proper plan. That plan can be forwarded to the servers and do some pruning. Okay, which server should I not query and which segment should I not query? What data is stored inside each segment? Broker doesn't know anything. Broker doesn't have anything on its case.